Hello guys, my name is Chinmay and this is my CWS project on maze solver. About this project, I'll be solving such mazes using DFS algorithm. DFS PC stands for depth first search algorithm, and this maze comprises of two integers 1 and 0. 1 denotes cells on which you can move, 0 denotes cells on which you cannot move. And you start at this corner, and your job is to reach this corner. And diagonal moves are not allowed, only downwards, upwards, right, and left out. And this is the kind of coordinate axis I'll be following for this. Depth first search DFS in the context of a maze solver. DFS depth first search is an algorithm that explores one route as deeply as possible before backtracking. This makes it a great way to find any path in a maze, but not necessarily the shortest one. So we'll be using recursion and backtracking here. Here is a small demonstration of the algorithm, and this is the maze. We'll be solving this, and these are the two solutions of it. So I'll check the first solution: a down, a right, down, down, a right, right, down, right, right, down. So this is the first solution, and it is indeed correct. And like D stands for down, U stands for up, L for left, and R for right. And here is a slightly bigger maze, and these are all the solutions of it. So, recursion. The recursion is the process of a process a procedure goes through when one of the steps of the procedure involves invoking the procedure itself. A procedure that goes through recursion is said to be recursive. So, an example of recursion is a factorial function. So, this is how a factorial function is defined, and factorial is n into n minus 2 into n minus n into n minus 1 into n minus 2 and so on till 2, so till 1. And just from looking at this, you can see n factorial is n into n minus 1 factorial. Now, like referring to the definition once again, when one of the steps of the procedure involves invoking the procedure itself. So when you're finding n factorial, you're also going to need n minus 1 factorial. So in the process of finding n factorial, you're also invoking this procedure again, but for n minus 1. So this is a recursion. It, uh, According to this definition, this is a recursion. And another example of a recursion is the Fibonacci sequence. Fibonacci sequence is sequence of numbers such that the ith number is the sum of the I minus 1th number and I minus 12th number. And start 0 and 1 are basically default values, or you can call them as base conditions. And based on these two numbers, the whole sequence goes on. Here you can see this one is the sum of these two. This 2 is the sum of 1 and 1. 3 is 2 and 1, and 5 is 3 and 2, and so on. Working of the code. First, we'll include basic functions which are contained in this IOStream module. Yeah. IOStream basically stands for input output streams, allows us to use gives us access to basic functions like cout and cin. Using namespace standard, basically this is basically used as a shortcut, because every time if we don't write this, every time we would have to write std double colon and cout. And we're including strings because our output is in the form of a string. We're displaying it as a form of a string. That's why. And include vector because our maze was a vector, and all of the solutions are actually stored in a vector. And this is our maze, and we also define another a 2D vector which contains values of the Boolean data type, and which are all initialized with false values. So this is the same dimension as this, and all is filled with all false values. And each like say 1 comma 1 cell of this matrix corresponds to 1 comma 1 cell of this maze. Okay, and we'll understand this when we understand the importance of this a bit later. And this vector string final path is actually used to store all of the possible solutions. Now, this is the main recursive function of our code. This its name is solve underscore RCN. RCN is basically recursion, and it takes three parameters: integer x, integer y, and a string path. So the first part of this if statement basically checks whether we are inside the maze or not. So x less than 0 will be somewhere here, y less than 0 will be somewhere here, x greater than maze size, maze dot size minus 1 is basically checking for greater than this is actually checking for this, and y greater than this is checking for this value, this region. So effectively all of this is basically checking whether we are inside the maze or not. And this part of this if statement is basically checking whether the current cell we are at is valid or not. So if that cell is 0, then that cell is not valid, or if that cell has been visited before, then that cell has not valid. We'll now understand the importance of this has visited. Why do we need has visited? To answer that, let us imagine our code without it. So let's consider this situation, this four cells of that matrix. Let's say you are here right now and you decide to move towards the right and then down and then left and then up. So in doing all of that, you basically are moving around in an infinite loop. There's a chance you can move around in an infinite loop. And with that, our basically algorithm is very inefficient if we don't fix this problem of infinite loops. To fix that, we'll use this has visited. Now let's imagine a code with the has visited. Say you start here, you mark this cell as true, and then you move to this cell, you mark this as true, you move to this cell, you mark this as true, then you move to this cell, you mark this as true. Now, if you try to move to this cell, but this cell is already marked true. This cell is already marked true, and hence a move to this cell will not be valid because of this if condition, this part. And hence we would be able to solve this problem of infinite loops. Now moving ahead, if any of these conditions meet, basically these are or functions. This condition is true, or this, or this, or this, or this. And if any one of them are true, basically then just return out of this. Return basically just what it does is basically exits out of this function. And then if our cell if our if we are basically inside of that maze, we'll then check if that the cell we are at right now is it an endpoint or not, endpoint or end cell rather, and has the coordinates maze dot size minus 1 and maze dot size minus 1 basically at the bottom right corner. Okay, if that is true, then we'll just push back our path, whatever this path we had given as an input, to the final path vector, and we'll just return out of this function. If the cell we are at right now is inside the maze and it is not an end cell, then we'll mark it as true, and then we'll explore in all four direction. First, we'll explore down and then up and then left and then R and then right. I'll explain this part right now. This is the coordinate axis that I'm following, which is y x plus 1 comma y is basically in the downward direction. That's right. And each time we are actually calling this function, we are updating this path as well. Like whatever like this path we are giving it, that we are updating it as well. Now let's understand the recursion part. Suppose this is the kind of situation we have a small part of this maze, and here the red dot cell which already have a marked value of true. So this cell is marked as true, this cell is marked as true, this is our current cell, and that is also marked as true, which I have not indicated because of to avoid confusions. This is our current cell right now, and we can move one place down right now. So if we move one place down, we'll be here, and this is marked as true. Now, we cannot move down again, because this, if we were to move down, this we would end up at this cell, but this cell is an invalid cell. And after down, we would move upwards, because once this function is called, and this if when this function is called, this if statement would be this if statement here, this statement would be true, and we would return out of this function, and then we would enter into this function when we'll move upwards. If we move upwards, if we try to move upwards, this we would end up at this cell, but this cell is actually marked true, right? So this is also an invalid cell. We can't move upwards hence, and we will now try to move towards the left. But again, the same thing happens here as well. This cell is a zero cell and is an invalid cell. And hence, finally, we just have to move towards the right. Okay. And this is basically used to backtrack. And I'll explain what backtracking is. In backtracking and its importance in our code. So, recursions are basically recursion is basically calling a function inside of another function. So, whenever you do that, let's say this is your main function, you call function f1 inside it, and inside f1 you call a function f2, and then f3, and so on till fn. And let's say, for example, fn is a function that returns it. This is the end of your recursion. So when this first f1 will return, and then f minus 1 will return, f minus 2, and so on, so on, so on, so on, so on. Then at last f1 will return. So basically, they're stacked in a way you can imagine it like this. They're stacked vertically upwards, and like they for the topmost one basically executes the first. It returns first. That's what I'm trying to say. Let's say the function fn is such that it takes an integer and returns an integer. Given by the recursive formula, output of fn is n times output of fn minus 1. And actually, this is the factorial function. So let's, in a general case, when an fi of call to another function fi plus 1 is made, a temporary block of memory is allocated to the function fi plus 1, and then a copy of the required inputs are passed to it. This is in the default case. The function fi does not resume execution until the function fi plus 1 completes execution. The functions resume execution from top to bottom. So to explain all of this, let's take an example. This is a code for finding factorial of a number. I have defined a function f that gives an integer and takes in an integer n. First, this is what I call base conditions. Base condition is basically used to stop recursions, prevent infinite recursions. So if we're checking basically when n equals to 0 or n equals to 1, we just have to return the value of 1, and as well as print this statement. And if this base condition is not met, then we would actually go and call fn minus 1 into n, because that was the formula. And when when all this records when the fn minus 1 basically returns a value, after all of that we'll print this function. See, we'll print this statement and we'll return the solution. Like, say this is in our code, this was the base condition. This we used this condition to avoid infinite recursions. Let's take an example with n equals to 5 here to understand this code. So let's say we need to find a factorial of 5. So f of 5 goes here. This base condition is not met, goes here, calls f of 4. F of 4, n equals to 4 goes here. This condition is not met. F of 3 is called. 3 goes here, condition is not met. F of 2 is called. 2 goes here, condition is not met. F of 1 is called, 1 n equals to 1 goes here, and this condition is now met. This condition is now met. This cout statement is printed, and this one is now returned. So f of 1 value is now 1, and since because of that f of 2 will also return 1 into 2. So and also once f of 1 is once this f of 1 actually has returned a value, this cout statement will also print for n equals to 2, right? So this is that statement, and similarly for 3 and 4, then 5. So this basically shows that like functions start resume operation basically in a top to bottom fashion. Now, to understand why backtracking is needed in our code, we'll take we'll look into this solution situation. For example, let's say for our algorithm first found out the first solution, like the marked with this red dot, and after finding the solution, let's say we didn't backtrack. So for if our algorithm were to find or to try to find the second solution, we would not be able to find a solution because this red dot cells containing these red dots would be marked as true, and we cannot use them in an attempt to find second solution. Hence, we would never be able to find the second solution. That's why whenever we either we reach the endpoint or we run into a dead end, we must like basically uh, reassign all of them to false values so that we can use these cells whenever we need to find a second solution, or basically look for the solution. I'll explain why we need it for a dead end case. Consider this situation where this is marked as true and this is your current cell right now. And since we are following this kind of sequence, we'll first try to move downwards. So we've moved one downwards. This is now true. This is the current cell. And then again we move downwards. This is marked true. This is the current cell. We can't move down. We can't move up. We can't move left. We can't move right. So if all of those fail, that means we run into a dead end. So this function will return, this function will return, this function will return, this function will return. Ultimately, we will have to execute this function. That means we'll just uh, exit this. Basically, we'll just mark this cell as false and just exit out of this function. And then similarly for xy corresponding to this cell's coordinates, we will also reassign a false value to this. And then once we have reached this cell, now we have an option to go up as well. Now, because all the subsequent functions called subsequent recursions calls called by this right here, this function have returned a value, move to this function, and hence we move upwards by 1 unit, and we are right here. So basically we went here, tried to explore this branch, we ran into a dead end, we backtracked back to this junction, and then moved back again. And again, moving ahead, this is another function. This returns a vector containing strings named solve underscore mean. Basically, it calls the solve recursion for the first time at the 0, 0 coordinate. That's basically a starting point with an empty path. Uh, and once all of this once all of them are returned a value, like all of this recursion is done, then we will return the final path. Final path basically contains all of the possible solutions of that maze. And inside the main function, we'll basically call this solve main, and then we'll store this final path inside of another vector containing string v1. And for string s in v1, we will basically print that string. We will basically print that string.
There is also a way to print the shortest path instead of printing all of the paths, though we would always get all the I will always get all of the possible paths. We're just printing the shortest length. Okay, so we'll define an integer len which is equals to maze dot size into maze dot size, which is n squared. The logic behind this is because the maximum possible length of a path would be n squared, and then next we are basically searching through the final path vector to find to find a like say path for which whose length is less than len. If that is true, then we basically assign len as that path's length. So effectively, this loop is basically giving us the minimum value of len, and then after that we have this cout statement, and then after that we have this another for loop that basically searches through the vector final path to print out any string s if that string has the same length as len. So basically, we'll just get a bunch of strings having this length, and that's the minimum shortest path. Basically, that's shortest path, and I'll show a demo as well. So here we have a really big maze. I'll just copy this over here, and then I'll just paste it here, and then I'll run this. And as you can see, we have got the shortest path. We've got two shortest. Thank you.